So far with Boolean algebra, we've talked about the functions that are available, and we've looked at the symbols for those functions and the graphical shorthand for those functions as well. But what good is this? This is just some abstract description of the kind of options that there are for combinations of variables of two values. What we want to do now is we want to start to look at writing some functions out and seeing how we can build machines that will accomplish those functions, and seeing some of the kind of things that we can do with them, some of the problems, mathematical and real-world problems that this kind of logic can solve. So let's start with one of the 16 functions that we saw there when we first, a few videos ago, when we looked at the possible functions of two variables, and there were 16 of them. Most of them had a common name, and or exclusive or not, whatever. But there were a few that were a little bit different. There was A prime B, and there was B prime A, I think there was there as well. So these are functions of two variables, right? F equals A prime B, F equals B prime A. A couple examples. Let's just take this one. How would we draw a circuit that accomplishes this? Well, we look at this and we say what we have to do first is invert the value of A, and then we have to AND it together with the value of B. So if we have A and B coming in here, we can't do this in a single gate. We have to have two gates, one after the other. So we can invert a gate, value of A inverted, and then AND it together with the value of B. So this is our first sort of multi-level circuit. And what we see is that we've got a circuit there where things will happen to these logical values step by step over the course of time. And eventually, at the end, we'll get our value F, which will be the result of that. Now this is fine, and this works okay. But we could find more complicated functions in this, right? Just like in regular algebra, we can combine functions together. We can add operations over operations. We could say A prime B or B prime A, right? For example, so this is another function, and it is the result of inverting A, and again, we can draw the circuit that it corresponds to, right? We invert A, here's A, we invert A, and then B happens to come along here. And then this is the same B as this. So what we want to do is we want to take that B, and we want to invert it here. Okay? And then we want to take the same A before we invert and put that there. Both of these are AND gates. So this is A prime B is ANDed together like that. B prime A is ANDed together like that. And finally, we take this result and we OR these together. And that's our final circuit. So this is F. So what we've got is two different ways to represent the same information. We have an expression, an algebraic expression. If you're used to seeing algebra, this is what it will look like. And you have a circuit that will do that. The neat thing about this is that this can become a physical object, where it doesn't matter what A and B are, the output F will be the function corresponding to this expression. And you can build a circuit for any expression that you write out. You can write out any random combination of any number of variables, and you can always build a circuit that will do that. Many of the simpler electronic devices that we see in our lives, like traffic lights, vending machines, anything like that, where there's buttons, or there's ways to measure the state of the universe, or there's timers to see how things change. There's logic that dictates what happens at certain times or based on certain conditions, right? If a certain amount of time has passed and a button was pressed, then the stoplight will change from red to green. If a sensor is triggered or whatever, if you have a vending machine, you put in a certain amount of money, based on the amount of money you put in, indicated by presence or absence of voltage on these inputs, a signal will be triggered that will allow or disallow a pop can or whatever to come out of the vending machine. Lots and lots of different special purpose individualized circuits are built using these techniques. You figure out an expression that represents the way that the world should change based on the value of these inputs, and then you build a device that will do that for you. A lot of early video games were programmed this way, right? A physical device corresponds to some relationship between values that are coming in. However, these can get pretty complicated, right? If you just put random connections down, they can get pretty complicated, and we already know that there are only 16 possible functions of two variables, and this wasn't one of them. So is there a way to take an algebraic function of any number of variables and simplify it, right? Just like we did in high school algebra, can we take an algebraic function and simplify it? Now, why would we do that? Well, in high school, you do that because your teacher tells you to. But if you're an engineer, you do that so you don't have to use as many parts. Because the simpler the expression is, the fewer parts, and possibly the faster and more efficient the thing will be, the less likelihood of errors, all sorts of reasons why you want to take an expression that corresponds to some processing of information and simplify it down to the easiest it can be. And the next couple set of videos will show some examples of the kind of simplifications you can do and what the results are when you draw this out in your circuit diagrams.